Welcome back. So let us look at conics in general. Of course, all the two-dimensional plane curves that we have considered so far are conics, and we'll see why we call them conics shortly. So here we are really just interested in their degeneracy. So there's a need for us to visualize this to see how we came about the term conics and what degeneracy actually means. So conics or conic sections simply means that all the curves that we've talked about so far could be obtained by taking or by cutting through cones, or when you set up a cone and try to cut through that cone using a plane. The shape that is going to be made is going to be, the possible shapes that you can get with that are what we call conics. So we will see that shortly. But we know so far that we can have from that a circle or an ellipse, which I said they are familiar, they are similar. And also we can have from that a hyperbola, okay, and you can also have from that a parabola. Of course, we considered four of them. Just as we said, these two are similar, so they're going to have similar derivations and properties and all of that. So, why do we call them conics? So let us see this illustration. I'm going to attach the link to this, okay, in the notes, or sorry, in the other section or other resources section of this lesson, so you can check there for the link. Just copy and paste the link on your browser and play around with this illustration. It's produced on it's on the GeoGebra website. So this is the illustration on the GeoGebra website. This is the author of this illustration, but it helps us understand the coding section idea. So we're going to make use of it here just to visualize what it feels like. Okay, this is a very good illustration. The fun about this is that we can play around with what we have here. So let us quickly see what we have here. Let's move the plane away. You can see this right here. This helps us to move the plane around. You can see the plane actually moves around the cones. Okay, so you have two cones here. The two cones are meeting at this end. So you can see that here. So we have this plane. We can move it around using this what do we call it now? Let's say this button. We can move it around using this button or slider, and we can change the orientation, that is the orientation of this code. Of course, we can visualize the different parts of this system by just moving it around with our mouse. Okay, so it's easy to visualize what's really going on here. So I think this is fine. So you see what we are really dealing with. This is two codes here, and you can see the position of the cone. This is telling us the angle at the center of the cone. So let's just leave it at the small angle. Let's leave it at, let's say, 40 degrees. I think that is fine. If you wanted the this cone to be wider, we would make something like this. This is something you can do using the GeoGebra software. If you have it, it's freely available. You can download and play around with it. You can actually make something like this for yourself, but that's not our business in this course. Okay, so this illustration just works perfectly for what we want to do for now. And this beta tells you the orientation of that plane. You can see the orientation of the plane. So if you want to get the angle between the plane and the vertical, you can see if it's at 0 degrees, for instance, it is vertical. So if you want to position it further, you want to move it, you want to move the angle to make it vertical, then we'll make use of this. And if it's at 90 degrees, we see that it is the horizontal. So that's basically what this beta is meant for. So we'll be playing around with beta and all of that. So you can see what is happening here. It's giving us the shape that is formed inside of this. As you can see it here, this shape that is formed inside of the code. If we try to visualize it here, we'll see that is exactly the shape we have here. Okay, that is where this plane intersects the code inside. We're going to have this shape up there. You're going to have this shape down there. Of course, you already know The conic section this is talking about, this is a hyperbola. We talked about the hyperbola before, all right? So it's going to form different things, and they already gave us illustration of how to form a hyperbola here and all of that. But really, it's quite easy to play around with and see for ourselves when it is going to form a hyperbola and all of that. So let's see. If we change the position of the plane, you can see that it does not change the shape that is being formed. So we change the position of the plane. You can see of the position of the plane. The hyperbola is still formed. The only difference is the shape of the hyperbola and all of that. Now, that is that for a hyperbola. It's quite easy to see how to form the hyperbola. What you should notice here is that the position of the plane does not impact the exact kind of conic section that will be formed. Okay. Of course, we see that it's going to form a hyperbola also. Now let us change this beta, for instance. That's the orientation of this. So we change the orientation. You can see at this point it loses contact with the plane below, and because of that, it now forms only one shape. And of course, this is our parabola. Can you remember how we talked about parabola? So once it forms this shape, if you now change, you can see that it is the angle, that is the orientation of this plane relative to the cone, that tells us or that determines the shape that it forms. It is not the position of the plane. So we can see if we change the position of the plane, it does not change the shape being formed. You can see it just moves from from a parabola facing up to a parabola facing down, but the whole thing remains like that. Okay. So we can see that actually at some point it can form a this is an ellipse, as you can see it here. So if we have this angle here, for instance, yeah, you can see the angle here forms an ellipse, and when we go up, you can see it extends out, and because this is no longer covered here, we see this is now a parabola. Yeah. So we can see that the position actually changes that. So I think that the position actually changes it. So when it's at this position, it forms an ellipse and all of that and all of that. So it's quite straightforward to deal with. All right. So what do we mean by, okay, we can already see that they are all conic sections. And of course, a circle will be formed when this thing is at 90 degrees. If it's at 90 degrees, you have a circle formed. So, and if you change the position, it will just continue or remain being a circle and all of that. So, it just changes the radius of the circle. So that is that. About that, you can see that all the um, curves that we've talked about, they are actually conic sections. Okay, that is what I mean by conic section. All right, because they are formed by sections of the cone as we actually cut through it. So you can see the plane is just like how you cut through the section of the cone. So anyhow you cut through the section of the cone, you're going to get a shape on that surface, a curve on the surface, which is going to be one of our conic sections. So that is that about that. Now, degeneracy. What do we mean by degeneracy? Degeneracy simply talks about what will be formed or what conic section will be formed if the plane actually intersects our cone at this center, the center where the two cones are joined. So if we change the position of this plane to the center where the two cones are joined, okay, is that the center right there? Is that the center? I think that's the center. Yeah. So I think that is the center. So we can visualize that this thing is at the center now. It's at the center of the two cones. If we put the plane here, and now we try to see what this is going to give us if we play around with the orientation. So when it is here, like this at the center, the different sections it will give us relative to when it is moved up or down is what we refer to as degenerate shapes. So the way it is now, the orientation is at 90 degrees. We know that normally when it's at 90 degrees, if we move it up, it is giving us a circle. This is giving us a circle. Move it up and down, it's giving us a circle. So a degenerate circle will be what will be formed when this thing is at that center. As we can see, when it is at the center right here, it is forming a single point. Everything converges to a single point. That tells you that for a circle, A degenerate circle is simply a single point, one single point. That is, all of those things will converge and will form a single point. So a degenerate circle is one single point. Okay, we'll talk about that analytically when still in this lesson. Okay, we'll do that shortly, but we already see that a degenerate circle is just a singular point. Now, let's play around further with something serious. Let's say that we change the orientation of this. Okay, we'll change it this way. Let's say that we have position our plane like this. The way that we can easily visualize, yeah, I think it's better this way. Now, let's move this up or down. You can see what it forms here. This is not a circle any longer. This is an ellipse. Okay, and that is not so obvious, but we can make it obvious. That is an ellipse. So when we move these up right here, you can see it's an ellipse. Move it down, it's an ellipse. So what happens at the center with this orientation that we are sure produces an ellipse down, produces an ellipse up. So what happens when we place it at the center? So when we place it at the center at this orientation, we see it also gives us a point. That means a degenerate ellipse is a single point as well. Just as a degenerate circle is a single point. It doesn't form any other shape. Okay. So we're done with that. Now let's talk about a um, hyperbola. So let us firstly get what will give us a hyperbola first. So let's change this. Let's change the angle until we're certain that we are getting a hyperbola. So this is a hyperbola. So we see that if we move this forward, we're getting the hyperbola. Move it backward, we're getting the hyperbola. So this is just giving us a hyperbola. So what happens when it is at the center, when the plane is at the center? So let's carefully do that until it's at the center. So we can see that when it's at the center, these 2 points will be joined. So you can see that when it is at the center, we are having or we are getting two intersecting straight lines. Two intersecting straight lines. That means that a degenerate hyperbola is two intersecting straight lines. Degeneracy is when the plane is at the center. So when we can see that when we move forward and backward is going to form a hyperbola, then we see what is going to happen when it's at the center. It's going to form two intersecting straight lines. So that is a degenerate hyperbola. We'll get to see what the equation of that is. But of course, we can already see that that is just what we get here, the asymptotes that we talked about earlier. So that is what the hyperbola will degenerate into. A hyperbola will degenerate into its asymptotes. So the equation of the asymptotes that we talked about before when we discussed hyperbola, that will be the equation of a degenerate hyperbola. So we'll see analytically how that comes about when we get there. Okay. So let's just move on. I think we've discussed ellipse, we've discussed circles, we've just discussed hyperbola. So let's see what is going to happen for a parabola. So for a parabola, let us change the position first. Change the angle so that we always get a parabola from this. Okay, so the way it is now, we know that we're starting to get a parabola. Let's see where we get a parabola. So this is a parabola. So if we change the position here, change the position, see that it still gives us a parabola. Anyhow, we'll put the position of this. It's a parabola, it's a parabola. So anywhere we are is a parabola. So we are good to go now. So what happens at the center? Look at the center, put it in the center. Can see that at the center it converges to a straight line. So that means a degenerate parabola is a straight line. And how do we know what the straight line will look like? You can see that it is just a straight line that will be through the axis of the parabola. So you can see that in any case, the axis of the parabola is going to be around here. So, and when we get here, we're going to see that this is just vertical. So we see that it's just a vertical line. And the vertical line to the parabolas we have been forming will just be the axis of the parabola. So that means that the parabola degenerates into its axis. and that straight line is what the degenerate parabola is going to give us. All right, so we know all the details now from this illustration. So let us go back to our notebook and see what the analysis is. All right, now, so that means that from our observation, we have seen that a degenerate or a circle or ellipse degenerates into a single point. It degenerates into a single point, that is 1 point. And of course, we talked about this before, but then we know that this could be generally written as x squared over a squared plus y bar squared over b squared. So it is when this combination is giving us 0, okay? When this combination gives us 0, I've spoken about this before, whether these two are the same, which is what we get for a circle, or they are different, which is what we get for an ellipse. Once we see that this other side is giving us 0, we know that is a degenerate circle or degenerate ellipse, because that is only satisfied by 1 point where this expression is 0 and this expression is 0. Okay, so that is that about that. And for a parabola, we've seen that a parabola degenerates into two intersecting lines. Degenerates into two intersecting lines, which are, of course, what we call the asymptotes of the hyperbola. Okay, and of course, we've talked about this before, that the asymptote of the hyperbola will be given by something like y bar equals plus or minus b over a x. Okay, we've talked about the equation of the asymptotes of a hyperbola before, and of course, this also follows from, or this obtains from, the equation of the hyperbola itself. We know the equation of the hyperbola is x squared over x bar squared over a squared minus y bar squared over b squared. So if this also is 0, we can move this to the other side and take the square root, and then the square root will be plus or minus, and then we'll make y the subject. It will give us this. So when this happens, we're going to have this. This shows that this degenerates into a two intersecting lines. One of them will carry the plus, the other one will carry the minus, which are those two intersecting lines, which form the asymptotes of the hyperbola. And in the case of a parabola, we don't have the standard equation of a parabola to be in this form, so it is not something we can just equate to 0 to get what it degenerates into, or to know if it degenerates hyperbola or parabola. Okay, so but for this case now, we already know that this degenerates into what again now? A straight line which is along its axis, which is the axis of the parabola. So if it's a degenerate parabola, it will just give us a straight line. So of course, we know the equation of a straight line is going to be something like y equal to mx plus c, or it will just be some linear equation or linear expression, or a first degree polynomial expression anyway. So that means that if a parabola is degenerate, so let's try and play around with that, because we cannot get that by equating some expression to 0 from the equation of the parabola, because it's not in this format. The standard equation of the parabola is not in this format, but we can reason that out from the illustration we did. We know that if this is the x-axis, this is the y-axis. If this is the parabola, for instance, we already saw that this was going to be y squared equals 4ax. The equation of this will be y squared equals 4ax. So if this is going to degenerate, it will give us this line. This will be the axis of it. And so what happens? That means that the degenerate parabola will just give us the x-axis, because it will be a straight line that is along this axis. And the equation of the x-axis is y equal to 0. So if that happens, that means for a degenerate what is it now? For a degenerate parabola, you're just going to have a straight line equation. It means that our a will be equal to 0, just like you have the what is now the focus here to be on the vertex, and of course that is going to form a straight line. So we're going to have y equal to 0 for that situation. So thank you for watching. That is the end of this lesson and indeed this chapter. We'll proceed from here in the next chapter.